Okay, well, thank you very much. I really appreciate the opportunity to speak in front of you guys. This is relatively new work with Vlad Vickl, and I'll try and tell you this story of shock formation from the point of view of sort of a fluids free boundary type problem. So even though it appears that I'll be focusing on compressible dynamics, which I will, there's this very strong component related to classical incompressible fluid analysis. Okay. So I'm going to focus this talk on isentropic compressible Euler equations in 2 space dimensions, just to give the simplest possible presentation of ideas. But everything that I'm going to tell you about will be true for the more general, fully non-isentropic system, and also in 3 dimensions, but the geometry is a little bit more tricky, so it's nicer to first see this in 2. Okay, what are the Euler equations? I'm sure all of you have seen this before. They're a system of conservation laws. You often see this written in what's called conservation law form. The first equation is conservation of momentum. U here is the velocity field. For us, it'll have 2 components, U1 and U2. Rho is the density, which we'll assume to be strictly positive. You can think of it as being around roughly somewhere around 1. And P is the pressure. And for this simple isentropic dynamics, we'll just take the gamma gas law. So pressure is 1 upon gamma, rho to the gamma. Gamma is this adiabatic constant. In air, it's about 1.4. Gamma equals 2 is the shallow water equations, which is a popular model to study. And gamma 3/5 is also interesting. There's sort of a lot of interesting versions of gamma, but you can sort of just think of gamma as being either 1.4 or 2 or somewhere around there. Now, okay, so this is the usual way you first see the Euler equations. I want to rewrite these equations in more convenient variables that somehow symmetrizes the equations a little bit. So we introduced this new adiabatic exponent. Instead of gamma, we're going to work with alpha. So alpha is gamma minus 1/2. So when gamma is 2, alpha is 1/2. And with this new adiabatic exponent, the sound speed, which you'll see classically as the square root of the derivative of pressure with respect to density, in this simple case just becomes rho to the power alpha, and this is a nice variable to work with. It's even nicer if you rescale it by 1 upon alpha. So our fundamental variables will be u and sigma. Sigma is 1 upon alpha times the sound speed. And what you see here is that this takes a very nice form. So if you just look at what these equations look like, partial tu, partial t sigma, u dot grad u, u dot grad sigma, and then alpha sigma, the same coefficient. Here it's grad sigma, here it's div u. So this is kind of a nice way of looking at the equations. Now, if you write this equation in sort of this classical form where you write it as a divergence of 2 fluxes, so we're in 2 spatial dimensions, you can write these terms as a partial 1 of a flux F1 and plus a partial 2 of a flux F2. And when you compute the eigenvalues and eigenvectors, what you see is that there are 3 wave speeds in this problem. So you can let n at this point just be any unit vector that you like, and you get 3 eigenvalues. And so there's 2 wave speeds, which are called acoustic waves or sound waves. If you start with a Riemann problem with discontinuous initial data, this slow wave speed corresponds to expansion. This fast wave speed corresponds to shocks. And then there's this middle wave speed, which is just the speed of the fluid itself. And that's where sort of vorticity waves and entropy waves live if you have entropy. And if you're dealing with incompressible dynamics, the characteristics associated with this wave speed are how we often do free boundary analysis in the incompressible setting. I'll say more about that in a moment. But I put this in blue. This is the interesting wave speed that where things will shock. So that's what we will focus on. So here's a picture which sort of tells the story geometrically. This, in fact, tells the entire story geometrically. So what am I showing you here? These are the three characteristics. So these are the characteristic surfaces associated with this fast wave speed. And they're parameterized in a particular way. So I'll say this again in a moment, but the x1, x2 plane is foliated by these straight lines where for each value of x1, you just have a line in the x2 direction. And from each of these lines traveling in the x2 direction, a characteristic surface emerges. And you can see time here is moving in the vertical direction. And these fast acoustic characteristics, just like you've seen in one dimension, they impinge and they get closer and closer and closer together. And the definition of shock formation for pretty much any system is that the distance between nearby characteristics, in this case, it's the three characteristic associated with this wave speed lambda 3 from the previous slide, the distance between these nearby characteristics is getting smaller and smaller and smaller and eventually goes to zero. So for this particular system of isentropic dynamics in two space dimensions, it's the three characteristic that impinges and creates the shock. If you were to plot the one or the two characteristic surfaces, they do not impinge, they stay perfectly nice. And so all of the action is associated with these particular characteristic surfaces. And in some sense, part of the understanding of how one wants to do this analysis is in trying to actually draw this picture. In some sense, once you've drawn this picture and you have a clear idea of what's geometrically happening, you've almost won half the battle. And what remains is to pick a nice way of describing the motion of these surfaces. So let me describe to you the basic program that we have in play here. The talk I want to give you today will describe a third of the program. And I'll discuss a little bit about, but its importance is in the context of the entire, completing the entire program. So let me sort of tell you the story. So here, what I've drawn for you is two sheets, two of these characteristic surfaces. So I've picked some value, so you can view a wave that's propagating in the x1 direction and is steepening. Suppose this is 0 in the x1 direction, and I've picked some value of positive x1 here and negative x1 over here, some values of the x1 coordinate. And the characteristic curve starts at initial time, which is going to be minus epsilon for us, where epsilon is some small number. It starts as the straight line in the x2 direction. And as you evolve forward in time, it forms interesting geometry. And then there's this initial time it's the very first time where these two characteristic surfaces have touched or come very close together at one point. And in the previous work that we've done, which I'll discuss shortly also, we wanted to classify this very first singularity. So here's this point in space-time is the very first place where you'll have gradient blowup. The gradient of velocity and sound speed will go to minus infinity at that point. And in some sense, you can sort of say, okay, that is shock formation. This point, we call it a pre-shock. This is where you have a Holder type of singularity. No discontinuity in the solution has formed yet, but classical solutions cease to exist exactly at this point. Okay, now what happens is, I don't know if you can see this, I've drawn these little dashed lines. If you move in the x2 direction, you can suppose this is sort of x2 equals 0 just for kicks. And as you move either to negative of that in x2 or positive of that in x2, there's going to be points that will also hit a little bit later in time, because this corresponds to where you set the maximal negative slope of your initial data. And then as you move away from it in the x2 direction, the slope is a little bit smaller, but it's still large. And in a little bit extra time, these 2 points will come together and they will form a pre-shock. And similarly, these 2 points will come together and they will form a preshock. And for these two-dimensional dynamics, what you have is a curve of preshocks, which can be parameterized by x2, by the x2 direction, if you like. So the program that we want to take part in is to show that we can construct solutions to the Euler equation in with this particular choice of coordinates, but it's still the Euler equations, where these solutions exist uniformly way past this time here. In fact, they'll exist up to this time here, which this BMD stands for beyond maximal development, as sort of just semantics. But it means that we can construct solutions which exist way past where this curve, as shown, is living. And what this means is that we will then be able to exactly classify this curve, its location and its time and so forth, by a condition on some geometry, which I'll again say in a moment. So that's really the first step of the program, and that's what I want to discuss today. That's called part A. Part B of the program is you can then do a little bit more refined analysis, and you can actually describe precisely what the Euler solution looks like along this particular curve of preshocks. And it turns out that it's one of these cusp-like surfaces. And the importance of giving a precise description, the importance of part B of the program, is in some sense the holy grail of this entire program, which is part C, which is to use information along this preshock as initial conditions for the so-called shock development problem, in which you start from continuous but cusp-like data that you've completely characterized analytically, and you instantaneously form a discontinuous shock surface together with two other so-called weak characteristic surfaces of discontinuity, which all simultaneously emerge from this curve of preshocks. So I can't see anybody's, when I'm in full screen, I can't see. Does anyone have any questions at this point? The best way to get my attention is just to sort of unmute and yell, because I don't think I can see people waving. So I'm gonna, anybody have any questions at this point? Okay. Okay, so that's the program. And I wanna make just a couple of remarks about this. So I think a lot of credit has to be given to Christodoulou, who was really the first to realize that some version of this program that I've outlined as A through C is necessary in order to develop the first theory of multi-D shock propagation. And I say this in contrast to a very long-standing program that's been in place, which you could sort of view as a generalization of the ideas that have been incredibly successful in 1D. So there's been a lot of work done in trying to understand Riemann data. There's been a lot of work trying to understand what kind of functional framework one can use in multi-D that would allow for shock propagation. And we sort of know that, for example, spaces of bounded variation are probably not going to work. And what I'm going to conclude with today is to sort of say that this idea of starting with Riemann problems is throwing away a great deal of information that I think Christodoulou realized one obtains by trying to classify the solution along this preshock and using that as initial data. So I'll say something about that at the end, although the focus of today's talk will be prior to that in terms of the evolution. The second remark, and in some sense my justification for taking part in this wonderful workshop, is that this really is, so this is in some sense related to what Jan was talking about earlier. Jan was sort of taking a problem in relativity and transforming it into this fluids type of framework or something like that. And what we want to do is to give this a very much a feeling of analyzing a classical fluids free boundary problem, as opposed to the sort of standard GR type of framework for this setting. And what I wanted to say was that while we're going to study the three characteristic, if you look at problems where the boundaries or interfaces are moving by the two characteristic, which is the common feature in incompressible fluid flow, such as water waves or physical vacuum singularity, fluid structure interaction, in lots and lots of scenarios, you'll see that basically the setting we're creating here is the three characteristic variant of the classic two characteristic fluids free boundary problem. The third remark I wanted to make, and I'll make more remarks about this later, but that it's possible to use self-similar variables, and we did this with Vlad and Tristan in a series of papers, to give a very precise and detailed description of the first singularity, which in this figure that I was saying, it's essentially, it's exactly at this point. And what happens is that one of the reasons that self-similar is such a nice system of variables for doing that, not only do you get a very precise description of the blowup, but you don't have to work that hard in the geometry, because the geometry of the fronts that you're creating in self-similar variables, thanks to the way that these variables are zooming in on the singularity, are really localized to that particular first blowup. And what this fluids-free boundary approach that we want to take shows is that we can give a very precise global geometry. So we're going to track a lot of features of the geometry by describing these surfaces very precisely, even when it's not so necessary, meaning prior to the singularity, but you kind of have to track them precisely so that, while the solution is still smooth, so that you can precisely track the geometry of the singular set. Okay, so now let me tell you the ideas. And it turns out that you can view this Lagrangian approach to characteristic surfaces really as an idea. This is really a motivation, because in a few slides, I'm going to tell you that we're not going to do this. But for now, I want to motivate why this is a really good approach to this particular problem. So here I've drawn, again, remember that we've taken our, let me just draw a little picture here. So here's the x1 coordinate and here's the x2 coordinate. And what we've done is at initial time, so this is t is equal to minus epsilon, we foliated this space with straight lines corresponding to values of x1. So there's, lots more than I'm drawing, but you get the idea. So that corresponds to how you start this surface. So then you propagate the surface by asking it to follow the three characteristic. And if you take this Lagrangian approach, what that entails is you can track not only the three characteristic gives you the normal component of this velocity, and there's also tangential motion. And so the Lagrangian picture is giving you even more information than just the motion of the three characteristic. It's actually telling you how particles are traveling tangentially along the surface, which isn't particularly necessary, but it's still interesting. So what you do is you say, okay, I'm going to look at the flow instead of the usual velocity that you do in incompressible. You follow the velocity associated with the fast sound wave. And you start the problem, so at initial time, you're at the identity. Okay, now here, this is a space-time picture of the surface. And if you take any time slice, which means you take your favorite time plane and you constant time and you intersect with that surface. So if you do it here, you'll get this blue curve. So this is the characteristic curve at a fixed time slice. And now you can ask yourself, how can I describe the geometry of that particular curve? Namely, how can I give it a tangent and a normal vector? And you're interested in curvature and in the metric. So you define this geometry. There's this natural induced metric. So when you see this notation eta comma 2 or any comma, so eta comma 2 just means partial to eta. So you're looking at the rate of change in this direction. And if this curve is just the image of a diffeomorphism eta, which so eta here has two components, eta 1 and eta 2, then eta comma 2 is a tangent vector. This gives the induced metric. And if you normalize this direction by dividing by the square root of the metric, you get a unit tangent vector. And if you do a 90-degree rotation, which is what this perpendicular symbol means, then you get the normal vector. And what this gives you is a very nonlinear equation for eta. But nevertheless, it's not too bad. So here it is. So this is encoding the normal vector. And you can see that this is a vector equation. It's for the components eta 1 and eta 2. And in some sense, I'll come back to this later, but there's going to be a better way of doing it, but I'm motivating it for this reason. Now, when does the shock occur? So you take the determinant of the gradient of this Lagrangian flow map, you call that J, and this shock here, this shock over here, this occurs exactly when J is equal to 0. So at the points x comma t, where this Jacobian determinant vanishes, that's where this curve of shocks actually occurs. And the comment is that the well-known criteria that a shock occurs via this Eulerian blow-up mechanism, namely the gradient of u goes to minus infinity and the gradient of sigma goes to minus infinity, this should be viewed really as a consequence of this Lagrangian picture. And it is. So what is the idea here? The idea is to develop a new system of variables for which you're going to write the Euler equations along this so-called three characteristic or the Lagrangian flow, such that the solution stays smooth for a much larger time interval than the curve of preshocks. And in particular, we're going to develop coordinates in which it'll sort of stay smooth indefinitely. Okay, so that's the idea. Now, let me motivate what's happening by returning to one space dimension. And what's really beautiful about one space dimension is that there's no geometry to the front. So instead of having a surface in space-time, you have a line, a curve. And then when you restrict to a time slice, there's no geometry. It's just a point. And so what used to be a normal vector here is gone because there's no geometry. And you just have that partial t eta is just u plus alpha sigma along the characteristic, along the three characteristic eta. So now eta really is the three characteristic in 1D. Now, if you define the usual Riemann variables, so you let, let me just wipe that out. There's no alpha there. That was a typo. Back to black. So if you define the usual Riemann variables as W as U plus sigma and Z as U minus sigma, you can define new types of Riemann variables, which it's not so clear why you would do this in one dimension, but I'll explain that again when we go back to multi-D. You define also the Eulerian, you define the Lagrangian version of this Eulerian quantity W prime. So W prime is just the derivative in the Eulerian derivative. So you define the Lagrangian version of W prime, and you define the Lagrangian version of Z prime. And then you can write the 1D Euler equations in the isentropic model as this system and this system. This is really quite beautiful, because if you just integrate this system, you see that the Lagrangian version of the Eulerian derivative multiplied by eta x, and eta x is playing the role of the one-dimensional Jacobian determinant. So eta x is just d eta dx. So this is the one-dimensional Jacobian determinant. This was J in the previous slide. It's telling you that this variable is just the initial condition. So this is as smooth as whatever your initial data is. If you take smooth initial data, this quantity is completely smooth. Nothing bad can happen to it, ever. Now, from the chain rule, you can sort of see that A to X Z math ring, this Eulerian Lagrangian version of Z prime, is also pretty smooth. But it turns out that Z math ring Z itself is smooth. Now, if in 1D, you can do some very fancy computations along a different characteristic. So if this plays the role of the one characteristic, you can get an explicit solution for Z prime along the one characteristic. And what this tells you when you go back to writing this along the three characteristic is that, okay, I'm leaving out some initial data stuff, but basically it's telling you that Z prime along the three characteristic is basically going like Z along the three characteristic. And it's using the fact that this is true. And so what this is telling you is that if you want to do analysis in 1D, and if you didn't have access to point-wise identities and you just wanted to do energy estimates, you have one equation you can do an energy estimate for, and you don't have to add any weights. You can just do a classical energy estimate by, well, you should use time derivatives. But every time you add a time derivative to your energy estimate, you don't have to change the weight at all. This object is smooth. And so you can basically show in this particular picture that this is smooth forever and this is smooth forever. And you can run this system for a much longer period of time than for your two characteristics in 1D to sort of meet. You can run this, you can run it for much larger periods of time. So that's the motivation for the new system of variables. Okay, so now that I've motivated the system of variables, I want to go back and say, okay, there's a problem, not really a problem, but there's this usual geometric difficulty that arises when you want to use Lagrangian coordinates, this Lagrangian coordinate eta, and sort of get the analog of this 1D system of variables that I just showed you. And I think Jan Brenier mentioned this in his talk. I think Camillo probably faces this problem in his geometric work, and it's certainly true for people working in shell theory, that when you use these coordinates where you have both normal and tangential motion, it's usually pretty easy and good to get regularity for the curvature, or the second fundamental form. It's often bad and kind of hard to get regularity for the first fundamental form, or the metric tensor. And this is indeed the situation that arises here. It's not impossible, but there's a better way of doing it. And in fluid dynamics, we call this the arbitrary Lagrangian Eulerian coordinate system, ALE. And in water waves, people do this all the time. And in numerical simulations, people do this all the time. The idea is this, that if you're only interested in the shape of your front, in this case, the shape of the characteristic surfaces, you have tangential reparameterization freedom. And the idea is to pick a better coordinate system where you remove difficulties in tangential directions and focus all the action on the surface moving properly in the normal direction. So here's how you do this. So let me just make sure. Does anyone have any questions at this stage, or? So far, so good? Okay. Okay, so here's how you do this. So again, we're restricting to a time slice. So take a time slice through that characteristic surface and you get a curve. And this curve is parameterized by x1. So I wrote this kind of funny. So this is gamma of x1. Oh, let me try that again. Gamma of x1 comma t. So t is fixed. X1 is fixed, and you have a curve that's parameterized by x2. And what you do is you say, okay, this curve here is a graph over the x2 axis. And I'm going to parameterize it by a certain height function, which we call h. So h is a function of x1, x2, and t. And this curve is literally this graph. And now I'm going to replace eta, the Lagrangian eta, with this ALE system of set of diffeomorphisms, which we call psi. And psi is just this graph function in the one direction and the identity map in the two direction. So here's the geometry now in terms of this graph. So now the induced metric is 1 plus h comma 2 squared. The tangent vector, well, if you take the, if this is the graph and you want a tangent direction, just differentiate with respect to x2. So that's h comma 2 comma 1. And now normalize by dividing by the square root of the metric. And the normal vector, again, you do a 90-degree rotation. And why this is so nice is now all of the action is reduced to knowing the dynamics of h. So notice that h comma 2 here plays a really fundamental role. This is partial to h. And this is really quite nice. So you now define the ALE versions of velocity and sound speed by these capital letters, capital U and capital sigma. And now you have to choose the dynamics of H in just the right way, such that it produces the dynamics of the family of diffeomorphism psi, which agree with the three characteristic in the normal direction. Okay? So what we do is we choose these dynamics. So partial TH is this square root of the metric times U dot n plus alpha sigma. H starts out, for each x1, it just starts out as being x1. So what this means is that, it means that h comma 1 at time minus epsilon is just 1, and h comma 2 at time minus epsilon is just 0. And you'll see I put this h comma 2 in red here. Whenever you see h comma 2 in any formula, you can think of it as being extremely small and hence 0, if you like, as a first approximation. So h comma 2, very small. You can almost think of it as being 0. And as I said, you choose the dynamics of this height function in such a way that the surfaces now move with the correct normal velocity, and there's this small tangential shift, which doesn't really change very much. And what we've won is we no longer have to deal with the two-component system, eta 1, eta 2. We, in essence, have to deal with the scalar h, and that's really why we do this sort of thing. And so, okay, so in this picture, what this is trying to say here is that if you take this time slice here, this is just the image of this time slice, which is the initial condition, the straight line. And this characteristic curve is really the image under this map psi. And now the Jacobian determinant, so you take gradient psi, which is a 2x2 matrix in this case, and you take its determinant, and miraculously, not really, by construction, you get partial 1h, or h comma 1. And this is really, really quite nice. So again, shock formation occurs when this Jacobian determinant vanishes. So the points xt where this vanishes tells you the location of the curve of preshocks. And again, we're using preshock as being synonymous for first singularities. Now there's a nice identity. You can use the chain rule. And if f is an ALE variable, which is the composition of an Eulerian variable with psi, then the normal derivative composed with psi is essentially the one derivative, but scaled by this object, which is blowing up. So j is going to 0 at a rate which we know precisely, and j inverse is blowing up. And this is essentially telling you that in these coordinates, normal Eulerian derivatives have this blow-up mechanism, whereas tangential derivatives are essentially partial to f. So tangential derivatives are really nicely behaved. Normal derivatives, as expected by construction, have this blow-up behavior to them in Eulerian. Okay, so what's left here? you have to set up a new set of variables. So here again, just to remind you, I'm sorry for the scrolling, but just to remind you, the goal here is to find the analog of this nice set of Riemann type variables, okay? And except for instead of using eta, we're going to use psi, which has the same shape as eta, but removes a certain difficulty. Okay, now the geometry, meaning the normal, the tangent vectors, the metric, they already have one derivative of the velocity and the sound speed. So if you want to play this game, you have to first differentiate the Euler equations once in Eulerian coordinates. So again, this looks hideous if you're not used to it. The comma k just means partial xk, if you like. Partial kj means partial squared, partial xk, partial xj, etc. So you differentiate the Euler equations once, but you're not done yet. You then have to change the transport velocity, which used to be u, into u dot n plus alpha sigma plus the tangential component, and then you have to subtract off what you just added here. And this is so that you can write the system. You're going to transform using this ALE variable. You're going to sort of get rid of these terms, but they have to be prepared to have the correct transport velocity, the correct normal component of the transport velocity. So again, you introduce the capital version of the variables as the ALE coordinate, and then wherever you see this math ring, that denotes that there's a derivative taking place. So you take, this is a 2 by 2 matrix. It's partial ui, partial xk. You compose it with psi, and you call this the matrix math ring uik. And so where you see two indices, it's a matrix. Where you see one index, it's a vector. So you take partial xk of sigma, you compose it with psi, and these are the ALE variants of the first derivatives. And now you introduce the Riemann type variables. So now the Riemann type variables have geometry involved. So these are the usual Riemann variables. This A is the tangential component of the ALE velocity. And these don't really play that much of a role in the analysis because the important variables are these objects with the math ring. And so these are the differentiated Eulerian variables. So you take this 2 by 2 matrix, you contract with the normal vector, and then you add to it the gradient of the sound speed, and this gives you a vector math ring wk. This is the dominant Riemann type variable, which will shock. This is the good Riemann type variable, which will stay smooth. So here, you take this 2 by 2 matrix, you contract with the normal direction, you subtract the gradient of the sound speed, and that's the good variable. And then finally, another good variable. This is like the tangential derivative of the velocity. So this is not like, this is the tangential derivative of the velocity. And this is this matrix math ring uik contracted with tau I. Now, okay, I'm going to overload you with notation. None of it is very important. Lambda 3 is just the fast wave speed, but written in ALE variables. So anytime you see a capital symbol, that means we've gone along the psi variable. V is a transport velocity, which pops up from time to time, and it's actually very, very small. You can, anytime you see V, you can think of it as being 0, if you like. It doesn't really matter. And now what happens is that with these variables in place, you can now write the evolution equations for all of the geometric quantities. So I told you that h comma 2 was really, really a nice quantity. And I told you everywhere you see V, you can essentially ignore it if you like upon first reading. But what you see is that the time derivative of h comma 2, this is a certain tangential derivative. If you ignore V, it's just the time derivative. It just goes like the tangential derivative of W and Z, or the tangential component of this math ring W and math ring Z. So remember, when you see the K, this is a vector. This is the derivative of W. This is a vector, the derivative of Z, and this is just the tangential component. So this is a really nice identity. It's basically telling you that with these new variables, h comma 2 has no derivative loss. You can then write the evolution equations for the unit normal and unit tangent vector. They're essentially the same as this. And again, no derivative loss at all. you can write the evolution equation for the square root of the metric. Again, no derivative loss. It's because h comma 2 is almost 0, it's staying very, very close to 1. So anytime you see a metric component, you can just think of it as being 1. And then finally, you introduce this metric scale Jacobian determinant. So this is the original Jacobian. This is the determinant of gradient psi. And you multiply by the 1 over the square root of the metric. This turns out to be a beautiful quantity. And this has this incredibly nice evolution law. And what's nice, this is really small compared to this, so you can ignore it. And it's basically telling you that the Jacobian determinant is behaving like like e to the time integral of the normal derivative of the first Riemann invariant. And that's kind of what you want. Okay, so Euler for shock formation. So this is, don't stare at this too long, it'll give you a headache. I'll write a much nicer version of this on the next slide. I just wanted to show you that you can write down this system of equations. It looks like it's a bit of a mess. It actually has incredibly nice structure. So here's the evolution equation for this Riemann type variable WK. This is the evolution equation for math ring ZK. This is the evolution equation for math ring AK. And just to give you a very brief reminder, what I'm claiming is that I've just written for you the system, which is the closest analog you can have to this beautiful and simple equations in one dimension. And in fact, it'll turn out to have very, very similar behavioral properties. Okay, but still it looks kind of ugly. So we just write the highest order terms, and we're going to use tensor notation so we can get rid of subscripts. So so where you see this bold W math ring, bold W Z ring, bold W A ring, that's what it means. So this is just contraction. So again, this is a vector, vector, vector. And now I'm just gonna, when I write LOT, that stands for lower order terms. These are terms that have no derivatives on them at all. So what I'm showing you here is, this is the evolution equation for W. And again, it's convenient, just forget about this V, think of it as 0. So it's telling you that partial TW multiplied by this weight JG, which is going to 0 at the pre-shock, has a derivative loss, but it's only a tangential derivative loss. And the same thing for Z, there's this tangential derivative loss, but Z actually has a normal derivative. So again, wherever you see h comma 2, you can forget about it. And what you see here is that there's this normal derivative, or one derivative, which is actually going to give us good regularity properties later on. So this is actually a nice term. And these blue terms, they actually talk to one another. So anyone who's ever done energy estimates on just the standard Euler equations, to work out short time energy estimates, there's a certain kind of cancellation that takes place. When you multiply this equation by W math ring, and you multiply this equation by Z math ring, and you use this identity here, these two terms exactly cancel this term when you multiply by A, which is essentially tau U. So these terms will cancel with these terms. The one derivatives, well, you multiply this equation by Z, you can form a perfect derivative and integrate by parts. So this is a really beautiful structure. How do we do these energy estimates? They're actually not so bad. But the key is, and this is again very similar to what we do in classical free boundary Euler type problems in the incompressible setting as well, is you work with a tangential gradient only. So namely, d bar plays the role of partial 2 and partial t. So our energy estimates are based on only differentiating in tangential directions. And so the main energy estimate term is this guy in blue. So you only need 4 of these tangential derivatives. You get W, Z, and A with 4 tangential derivatives weighted by a half power of this Jacobian determinant in L2. There's a damping term that arises where you get L2 in time control with this 1 over epsilon prefactor, and there's no Jacobian weight, determinant weight here. I'll explain that in a moment. And then these are these elliptic type estimates where you can control one derivatives, the normal derivatives of Z and A, but nothing like that is necessary or appears for W. So where does this damping term come from? Well, remember, I told you that there was this very beautiful formula for the Jacobian determinant, which involved JG, the vector W math ring, dot with N. And when you look at this equation here, or this equation here, and you do energy estimates, you have to commute the JG around the time derivative and around this transport operator. And when you do that, you get this multiplying, whatever highest order derivatives in your energy that you're trying to get. And then you make the observation that when you take this W equation and you take its normal component, that modulo some really tiny terms, you basically get this beautiful identity that, again, think of V as 0, the time derivative of JG n dot W is 0. And this is telling you a very beautiful identity. This is as close to one-dimensional dynamics as we can get. It's telling you that JG times n dot W math ring is going like the initial data. So this quantity is smooth. And when you take initial data, you want to sort of start the problem in order to get shock formation. You want to start the problem where you give it a maximally negative slope of -1 over epsilon at some particular point. And there's a region in space-time in which this quantity, which is equal to this quantity, satisfies this particular point-wise formula. And it's from here that you get this kind of damping term because of the sign definiteness of. So a lot of green, but I just wanted to give you an idea. Okay, so that's basically where the damping term comes from. Let me just sort of say just a couple of things about this. So the energy estimates are done with only 4 tangential space-time derivatives. That explains how you get this norm. I explained how you get the damping. These additional 1 derivatives on Z and A come just from the structure of the equation. They're essentially elliptic type estimates, and they just follow from the structure of the equation. So everything in blue is controlled by this basic energy norm, and then what's in magenta is coming from the equation and gives you these additional norms in our energy function. And as I said before, this is exactly how we study classical fluids free boundary problems, but along the 2 characteristic, where it's a lot easier in some sense. Okay, so what's the main theorem? I'm not going to give you this is a very rough version of the main theorem. So for an open set of data with maximal negative slope, partial 1 W naught, which is the initial condition, at space origin 0, set to -1 upon epsilon. So that's the largest negative slope you can have. There exists a time interval, which is roughly, it starts at -epsilon, and you can go up to time epsilon. You can actually go much further, but I'm just writing it this way. There exist smooth solutions to this WZA system, such that you have these energy norms are essentially bounded by a little bit more than the initial data. And there exists a computable curve of preshocks defined by the condition that the Jacobian determinant vanishes. Now, the point here is that if the first singularity, there was this curve that I drew for you, and this was the first point where the characteristic surfaces touched. And this is roughly happening at time 0, plus or minus epsilon cubed. And we can go much further than that. Oops. I don't know how that happened. We can go much further than that up to time epsilon, but in fact, this is just for convenience. We can actually extend the time of existence indefinitely. Now, we only need 4 tangential derivatives, but it turns out that 3 is probably enough. It's just that the proof is a little bit more tricky, so we just decided to go with 4. And an important remark here is that there's actually no need for generic data to construct the full curve of preshocks. You need it in order to classify the solution along the preshocks in an appropriate way, but just to prove shock formation all the way up to this entire curve of preshocks, you don't need it. And what generic means is that when you set this slope to be -1 over epsilon, that it's a global minimum. So when you construct generic data, you ensure that this is a global minimum. Otherwise, you don't. And you don't have to. That's the point. Okay, so I was actually motivated by Jan Bernier's talk today to sort of say a little bit about Christodoulou's method. So I just added these slides, and I've never actually given this talk before. So I have no idea how long this is going to take, but there's only a couple of them, so I think I can finish. So I wanted to sort of put this approach into and sort of compare it against Christodoulou's method, which is this very much a general relativity approach. So here's this is very much related to what Jan was talking about this morning. So if you consider a Lorentz metric, this is often called the acoustic metric, and you can write the components of the inverse metric like this. Unruh in 1981 and Vasseur in 1993, they proved that if you consider the velocity potential phi of an irrotational compressible fluid, that it satisfies this wave equation with respect to this Lorentz metric. And in this geometric picture, you can view sound waves as photons, and they follow the null geodesics of this acoustic metric. So just think of the light cones in relativity. And this is the remark that we made this morning. Jan said this as well. It's really remarkable that even though the underlying fluid dynamics are Newtonian and non-relativistic and take place in a flat space-time, the sound waves are governed by a curved Lorentzian space-time geometry. And this opens the door to studying irrotational fluids the same way you would study, the relativistic motion. So these null geodesics, they're bicharacteristics, and they're obtained as solutions to this Iconal equation. And if you've never seen what this Iconal equation looks like, this is it. It's a space-time equation, and this is sort of like a second-order wave equation, Eulerian counterpart. Okay, it's not exactly a second-order wave equation. It's like an Eulerian counterpart to a transport equation. So it's very similar to if you were to, in like the classic fluid community, you might sort of solve partial TQ plus lambda 3 grad Q is equal to 0. There's also some information. You'd have to multiply this by something like partial TQ plus lambda 1 dot grad Q. So this product, but roughly speaking, this is almost like transport. And this sets up the geometry of these space-time characteristics that I showed you, but in kind of an Eulerian way. So Christodoulou used these Eulerian-like tangential and normal derivatives by once you have the gradient of Q, you have the normal and tangential direction. And then he employed energy estimates, which require weighted normal derivative operators. So every time you differentiate in the normal direction, you have to add an additional power of something like JG. So it's an Eulerian-like version of applying this object as many times as you're going to apply an energy method, K times whatever. And because the tangential normal directions are tracked throughout evolution, it is possible to continue the solution past this first singularity, and you can capture in principle the maximal development until, the maximal development is you basically track each trajectory until you can't go any further. Something is blown up. So that's essentially this picture that I keep drawing. So Christodoulou proves that there exists at least one point in space-time at which a preshock forms. And in his book, in the original method, there's a very large and perhaps indeterminate number of derivatives that are employed. And Jared Speck, Luck and Speck, they're really experts on Christodoulou's method. And they generalized it a little bit to add vorticity, because Christodoulou's work was for irrotational flows, both in the relativistic and non-relativistic setting. And Luck and Speck were able to add vorticity, and that method, their method requires 22 derivatives for the 2D isentropic Euler system. And that's not very surprising. In our self-similar work with Vlad and Tristan, we use something like 18 derivatives. So it's not so uncommon to need a large number of derivatives, if you're going to track all the derivatives. And in some sense, the beauty of our variables is that we can get away with just tangential derivatives. And this is really what keeps the derivative count essentially to the Sobolev embedding level. So it is not necessary to use generic data to prove shock formation, but it is necessary to use generic data to give a precise description of the solution along the curve of preshocks. And the remark here is that if you read a lot of these review papers that you see about shock formation, there's this conflation of two ideas. So it's often discussed that Alanak used a blow-up profile, and because he used a blow-up profile, which was generic, namely it had a local it had a maximal local minimum, that in order to use a blow-up profile, you had to use generic data. And because you use a blow-up profile, you're only getting self-similar blow-up profile, you're only getting blow-up at one point. And this was somewhat restrictive, it was thought, because it precluded the possibility of maximal development. But these are really two ideas. So you can use blow-up profiles without a generic data, and you can certainly capture the full maximal development. In fact, as we go beyond maximal development with generic data, they're completely unconnected. Okay, so I'm just going to summarize the ideas of the proof. So one, we use an ALE free boundary approach to the global geometry of fronts. Two, we have a new idea, a new type of differentiated Riemann type ALE variable, which allows for a simple energy method with only 4 tangential derivatives. Three, our Euler equations and these ALE variables have solutions that extend beyond maximal development, meaning they go way past the curve of preshocks where everything blows up in Eulerian. So up to maximal development, our ALE solutions agree with Eulerian solutions, but our ALE solutions can be extended indefinitely. And once you extend them past the curve of preshocks, they're no longer physical. You can't go back and forth. But nevertheless, they're well-defined solutions which allow you to come back and say, okay, now that I have this uniformity in my bounds, I can just tell you where the Jacobian determinant vanishes, and that classifies the curve of preshocks. And again, finally, our energy estimates with 4 tangential derivatives are combined with some cute little pointwise bounds on tangential derivatives of geometry. That's not really that surprising. So, okay, there's some basic properties of geometry. I don't really want to say too much about that. I'll just have one quick slide and spend 30 seconds just explaining why the energy methods are so nice. So this is color coded. The magenta terms give you damping. They're really nice. The orange terms give you anti-damping. They're not so nice. And the blue terms require cancellation with energy estimates. So you take 4 derivatives of the equations. I've written that here. You take the inner product of this equation with this, of this equation with this, of this equation with this, and you go to the races. And there's a weight here. Sigma is the sound speed. You can think of it as being roughly 1. You multiply by a negative power of beta. And that negative power of beta gives you terms like this, which fight the anti-damping terms, which are sort of scaled like alpha. So if you take beta big enough, I think like, I don't know, -2 or 3 is enough for the kind of gammas we were talking about, the kind of adiabatic exponents we were talking about. You get exactly this energy inequality. And once you have this energy inequality, which gives you tangential derivatives on all variables, and then elliptic estimates give you the normal derivatives on A and Z, you can get pointwise information on this variable by using this basic identity. So it's telling you that the Eulerian normal derivative is scaling exactly like 1 over the Jacobian determinant, which we have precise information on. So now that we have shock formation, where does this lead us? So I just have one more slide. Our bounds allow us to construct this curve of preshocks as the set where JG is equal to 0. And this was what we proved in part A. So today's talk basically said, we have solutions that go way up to here. We can construct this curve of preshocks. We're kind of set. In part B, which is the next thing we're doing, is that we go to 5 tangential derivatives. So that gives us 6 derivatives on the original variables and by Sobolev embedding C4. And this allows us to use generic initial data where this slope condition is a global minimum. And now the 2 conditions that the Jacobian determinant and the gradient of the Jacobian determinant vanish on this curve C are enough to give us a complete description of the fact that the Euler solution restricted to this preshock is essentially a C1/3 cusp surface in the normal direction. And why do we do this? For the holy grail of shock development, we want to be able to construct discontinuous shocks in multi-D. So the point of getting precise analytical information about the solution along the preshock is that we use that as initial data for the shock development problem. And this was Christodoulou's very important observation. So if generic data is used, then we get a C1/3 surface as an initial condition for the development. This allows us to do an analysis in the development phase where you use two derivative analysis weighted appropriately. The geometric entropy conditions allow you to select the correct roots of polynomials which arise from Rankine-Hugonian jump conditions, and you can actually establish uniqueness in a class of this type. There's a shock surface and 2 weak characteristic surfaces of discontinuity that simultaneously emerge. And Vlad is going to talk about this on Friday in the case of azimuthal symmetry. If you have non-generic data, then you obtain less regular C1K pre-shocks. And as K gets larger, more information is lost. And what happens is that as K goes to infinity, you recover Riemann data along your pre-shock, but too much information is lost. And as Camillo and his co-authors have shown, even entropy conditions aren't enough to recover uniqueness in that class. So that's pretty much the program. Let me end here, and thank you very much.
Thank you very much. Are there questions? Anybody online? I can't actually see. If you have a question, just raise your hand. Otherwise, we're not able to see the chat from here. Okay, I mean, it seems everybody is looking forward to the second part of the by Vlad. So, okay.
So in Lagrangian coordinates, what do you have collision of particles, or what is happening at the Lagrangian picture?
Yeah, and the Lagrangian picture is the same as the ALE picture. Your characteristic surfaces collide, and they collide along that curve that I was drawing. Let me just go back. Yeah, they collide along this particular curve. But what happens is that each surface just keeps extending. It doesn't actually care that it collided with anything. Nothing blows up. The only thing that happens is that this object goes to 0 at that along this particular curve. but nothing bad actually happens. And so once they collide, you can continue the solution where the surface they pass through each other, and they're no longer physically representing any fluid dynamics, but they allow you to have uniformity in your bounds, which then says, okay, now that I know the solution exists up to here, I've covered this entire curve. I can just check where this Jacobi determinant vanishes, and you can describe the location precisely. But so yes, you have collision, they pass through each other, but in the equations, in the solution, nothing bad happens. There's no blow up. It's as though they don't see each other.
Okay, so there are no more questions. Thank you very much, Steve.